So the other night I'm doing the dishes and I get a text from a friend of mine saying that she heard something about some UFOs, like these lights flying across the sky in a straight line. And then her daughter had gone outside that very night for a walk and she saw this string of UFOs flying in perfect single file formation across the sky. Yeah, it's Starlink. Yeah, but then it was doing this and it was moving. Yeah, it's Starlink. Well, how do you know? Because if we don't do something about Starlink soon, it's going to ruin astronomy. Now, I was being maybe a little bit hyperbolic, but, like a lot of astronomers, I have a love-hate relationship with the whole idea of Starlink. I mean, as a person who uses the internet, I love the idea that they are going to be able to bring broadband service to the world at very low cost. But as an astronomer, I'm well aware of the challenges that many observatories are facing by having these unexpected streaks showing up in their images. And the streaks are a little bit more than just an annoyance, they are a real problem that has to be dealt with. Now, it turns out that SpaceX have actually been pretty candid and upfront about wanting to reduce and, in fact, ideally eliminate any adverse impact they may have on astronomy. But first, before we get into all the mitigation efforts, we may as well just kind of quickly recap just what Starlink is all about. Starlink is designed to put together basically a huge mega constellation of satellites that can provide low latency internet. In other words, think of internet basically traveling at the speed of light. Right now, we do all that using fiber optic cables, which are laid across the ground and even under the ocean. But light travels up to 50% slower through fiber optic than it can in a vacuum. So if you could have a relay of spacecraft that are flying in very low Earth orbit, you can get very low latency internet, and even better, they can provide that internet access at low cost to people around the globe, including the majority of the human population that don't have internet access at all. Now, normally when we think of using satellites, we are often thinking of the low Earth orbiting satellites. These are spacecraft that typically operate at altitudes of, 1,000 or more kilometers above the surface. The problem with using those types of satellites are twofold. First of all, you have a longer travel path for light to take from the ground to the spacecraft to the ground again. This is actually going to result in a longer latency period than just using old-fashioned fiber optic. The second problem is orbital debris. I mean, these spacecraft are supposed to deorbit after their mission lifetime, but if for whatever reason they can't bring the spacecraft down on command, then they have to just wait until the orbit just naturally decays, and the higher up the spacecraft is, the longer it's going to take for its orbit to decay. So you end up with a whole bunch of unwanted space debris. But SpaceX is going to do something different with Starlink. They're operating them at about 550 kilometers. And this has two advantages. The first is that it has a shorter path for light to travel, so you get lowest possible latency. And the second is the fact that it is deeper in the diffuse outer atmosphere of the Earth, which allows them to deorbit pretty quickly once their mission lifetime is over. However, the closer the spacecraft are to the surface, the smaller their field of view, and therefore you have to have a network of satellites essentially crisscrossing each other all around the globe in order to act as a relay for data from one point on the ground to another. And this results in a lot of satellites. How many? Well, SpaceX's initial plan is for 1,584 of these satellites. That is phase one. But eventually, they'd like to raise that number to be higher, as many as 42,000 of these satellites. Now, these satellites are first deployed at an altitude of something like 300, maybe 350 kilometers above the surface. That's actually too low for their operational orbit. They're actually trying to raise them by about another 200 kilometers or so. So they spend the first few weeks of their mission just raising their orbit using some tiny ion thrusters, and these thrusters are very low thrust, so they have to spend a couple of weeks getting themselves up to that operational orbit. While they're flying in the orbit raise configuration, they're trying to keep the spacecraft as flat as possible. So that means each individual spacecraft deploys its solar array, but aims the solar array down along the direction of their travel so as to slice through the atmosphere with as little drag as possible. However, it's these solar panels plus the body of the spacecraft that are reflecting light back to the surface, and so we initially see these as the bright string of pearls that cross the skies over time. Over time, though, the orbit does get raised, and by the time it reaches its operational altitude, it's now able to transition to its on-station deployment, and the solar array raises to a vertical configuration called a shark fin. Now the solar array is able to provide the maximum amount of power to the spacecraft, and the spacecraft is reflecting far less light to the surface. Now, it's important to point out that these satellites are only going to be visible during the twilight hours after sunset and before sunrise. That's when the sun angle's just right to catch a glint of light reflecting off of them back to Earth. Once twilight is over, you really don't have to worry about them too much. But during the orbit raise period, the satellites are very bright. They're as low as third magnitude, and sometimes people have seen them even brighter. Once they get on station, it's a lot better, but they're still kind of bright at magnitude 5. I mean, that is certainly faint enough to be invisible from urban and suburban regions, but telescopes operate under very dark skies, out of the cities, on purpose, right? Just to avoid light pollution. So even fifth magnitude is still plenty bright to saturate our detectors. So one way to mitigate is to just wait until after astronomical twilight to start your observations. But then you are giving up precious observing time, and that's especially a problem during the summer months when the nights are already at their shortest. But the Starlinks are definitely bright enough to saturate detectors and even create ghost images, and that can just render entire observations useless. Now, one way to mitigate this would be to at least have some advance notice as to where the spacecraft are and where they're going to be, so that you could take short exposures and try to avoid as many of those satellite streaks as possible. That might be doable with 1,584 satellites, but when you get to 10,000 or 20,000 or 42,000 satellites, it's really just no way we could think of to actually overcome this. Now, if your field of view is small enough, then maybe you do have a chance at avoiding some contamination. Maybe you'll just get lucky. But if you're doing like a wide survey, like the dark energy camera, then you're just going to get streaks that are going to render entire data sets useless. In fact, no other observatory is going to be more affected by Starlink than the Vera C. Rubin Observatory, which we formerly used to call the Large Synoptic Survey Telescope, or LSST. Its job is to scan the entire sky for a decade, looking for anything that moves or changes brightness, anything that might go bump in the night. To do that, it uses an ultra-wide-field camera that is larger than 40 times the full moon, and it will take up to 2,000 exposures a night and just systematically scan the sky for anything that's changing. Among those things would be finding new asteroids, which could potentially pose a hazard to Earth. So the last thing we want to see happen is our ability to protect ourselves from an asteroid impact because we have too many satellites in the way. Now, I do want to say that I don't think SpaceX is really the villain here, because they've been on the record as trying to mitigate their impact to astronomy. They're well aware of the problem. And yeah, Elon Musk got a little bit of heat because his initial response was to say, well, let's just put telescopes in space and not have to worry about that. But that just isn't going to work. I mean, read the room, man. I mean, come on, that's not going to happen, right? It turns out launching a telescope into space is really not the cost driver. It's really operating the telescope, designing it, building it, and operating it that really costs a lot of money. Ground-based astronomy is always going to be cheaper and easier to manage, both on smaller and even on some larger scales. Plus, you just get to have bigger telescopes that way, which are necessary for things like the Rubin Observatory and others. Anyway, SpaceX has made it clear that their goals are twofold. First, they want to reduce the naked eye visibility of the satellites from a few weeks to basically down to like 1 week. So minimize the amount of time that the satellites are really, really bright. The second goal is then they want to keep the satellites as dark as possible, even when they are on station, in order to prevent any contamination. To that end, SpaceX actually spoke last week at a meeting at the National Academy of Sciences to a panel of astronomers that were trying to work out mitigation strategies against these mega constellations. It was a private meeting, so there's no recordings that are being made available as far as I know. But they did release some slides, and they also produced a really cool article, and they have that on their website you can check out. I'll put a link in the description. But they basically outlined what they're trying to do. So, for example, when the spacecraft are operating on station, they want to reduce the reflection on antennae during both sunset and sunrise. And then during the orbit raise, they want to change the orientation to reduce the reflection of both the antenna and the array. But they've also been experimenting with a darkened version of one of their satellites. They call it Darksat, and up until now, they haven't really talked about exactly how they were going about treating this particular spacecraft. But now they have. Now they're telling us what they have been up to. They have these phased array antennae. These are the white squares that you see at the bottom of the chassis of the spacecraft. This is the part that faces down to Earth and relays the communications between spacecraft and ground stations. And they took one of those and they treated it with a darkened material. And they were able to reduce the apparent brightness by a fair amount. They more or less cut it in half, which is really a good start. However, a dark spacecraft absorbs sunlight rather than reflects it, so it starts to heat up. And that can result in a overheating spacecraft. And not only that, but can also turn the spacecraft from a bright optical source into a bright infrared source. So if we're trying to do infrared astronomy, we can still get these very bright satellites flying overhead, just radiating as infrared. So what they are hoping to do instead is introduce a visor mechanism. They're calling it Visorsat. And the intention here is to just deploy these kind of like foam-like visors that are transparent to radio, but otherwise will just be opaque to visible sunlight. They're also going to change the orientation of the spacecraft during the orbit raising part of flight. They're basically going to roll it 90 degrees along the long axis of the spacecraft so that any sunlight striking it will just be glinting off the very edge of the panel, and that should keep the spacecraft fairly dark as well. Now, will this work? Well, the only way to find out is to test, and to that end, SpaceX have already begun developing a newer, improved version of Darksat. They're already looking at future versions of spacecraft designs that will further reduce their cross-section and keep them even darker. These spacecraft are going to be replaced every 3 to 4 years anyway with upgraded next-generation versions. So over time, I would like to think that this problem can if not completely go away, because it never will, but at least it'll be mitigated enough that it won't really have a lasting impact on astronomy. But we're also going to have to work out ways to mitigate from the ground as well. So, for example, the Rubin Observatory said that they are working on a way to reduce the amount of ghost imaging during a satellite streak. And we're probably going to have to come up with some very sophisticated models that will help us to predict exactly where the spacecraft are going to be at any given moment and time our observations appropriately. That's, of course, going to result in a degradation of science efficiency, but hopefully it's something that we can live with, and hopefully it won't get any worse. I do want to say, though, that, at the end of the day, look, we don't have a choice. I mean, Starlink is coming, and it's not just Starlink, but Amazon are doing this, and there's another company that's out there doing it, and who knows, that's just what's happening now, but who knows what's going to happen 5-10 years from now when other companies start getting into this marketplace as the technology becomes cheaper and cheaper. So at least SpaceX, to their credit, they're not under any regulation, by the way, to support astronomers. I mean, we actually have regulations in place to mitigate against interference with radio astronomy, but we don't have any regulations in place for optical astronomy. So, SpaceX are at least stepping up, and they're going to probably be the largest players in this space. I mean, they're going to have the largest constellation of these types of satellites. So I'm glad that they are helping out with it. But, I know that these string of pearls that we see in the sky from time to time are kind of cool, but I think everybody would get pretty irritated if they walked out at night and saw nothing but satellites crisscrossing overhead. I mean, I think that's going to get pretty old pretty quick. And to their credit, SpaceX seems to understand that as well. So we'll just have to see what happens, keep trying out new ideas, seeing how we can mitigate against this, and just making this work better. And by the way, the Rubin Observatory, i.e. the LSST, is a really exciting project. So if you're not familiar with it, I invite you to take a look at this video that I'll have right here. So take a look at that when we're done over here. And I do want to thank my Patreon supporters for helping to make Launchpad Astronomy go, all for the price of a cup of coffee every month. So if you'd like to help out, please feel free to check out my Patreon page. And special thanks as always to my cosmological supporters, Stephen J. Morgan and Michael Dowling. Thank you guys so much for all of your help. And if you would like to keep informed on the goings on with SpaceX, Starlink, and most of all, the universe in general, please do make sure to subscribe and ring that notification bell so that you don't miss out on any new videos. And until next time, stay home, stay healthy, and stay curious, my friends.